third harmonic is 3 times the fundamental frequency. Okay, so, but in this lab we're only going to be dealing with the fundamental. And so this length from here to here, we're going to measure that. And this length basically is now equal to lambda divided by 2. Okay, so it's half the wavelength. That's going to, when we pluck it, it's going to be half the wavelength. Okay, so now remember, okay, the frequency times the wavelength equals the velocity of the wave. Okay, the velocity of the wave traveling down the string. Okay, so what we're going to do is we're going to solve for, so 2 L equals lambda over 2, so 2L equals lambda. Okay, so I'm going to come over here and say that the frequency, there's the frequency, okay, and the lambda is really twice the length. 2L equals V wave. That's V. Okay. So now I'm going to plug all this into here. So I'm going to say that frequency times 2L, that all of this is the velocity of the wave, and it equals T over mu square root of. Okay, that's F times L times 2. Okay. So what I'm going to do now is I'm going to solve for F. I'm going to divide by 2L, and I will get, and I'm going to break this up, and I'm going to say this is the square root of T divided by the square root of this mu constant. Now I'm going to say F equals 1 over 2L square root of this constant, okay, times the square root of tension. Okay, so notice, now you say, well, why are we doing this? We're doing this, I'm going to erase this right here, because what we're going to do is we're going to pluck the string at different tensions. And then after we pluck it at different tensions, notice if I take this data and I plot on the horizontal axis the square root of tension, plot the square root of tension, and on the vertical axis I plot the frequency that I generate. So we're going to add different weights. Okay, we're going to get a couple of points here. We're going to fit a straight line through that. Because notice that the frequency is linearly related to the square root of the tension. Okay, and what is the slope? If we take as we increase the tension, we increase the frequency. Okay, and it's a linear relationship between the square root of tension and frequency. The slope here is equal to 1 over 2L times the square root of this mu term. So the whole point of this lab is to increase the weight, measure the frequency, and see if in fact it is more or less a linear relationship. It should be, and then we'll calculate the slope. Okay. So if you look at page 10. At 10, we're going to collect the data. We're going to probably take 3 or 4 measurements. We're going to increase the tension, and then we're going to measure the frequency. And then you can make a plot like this. Okay, and I have, you can make a plot like this, and then you calculate the slope. And you follow the instructions on page 11, and you can calculate what this mu constant is. Okay. Okay, now question, now that's that portion of the lab. Now there's one more question, and that's on page 12. And I'm going to go over that just real briefly. This is something that I'd rather, you can do it by hand, but you can also do it much quicker in Excel, and I'm hoping you'll do it in Excel. Okay. What I want you to do on question 8, page 12, this is a numerical kind of a numerical kind of question, and basically I'm giving you you have two sinusoidal curves. Y1 is A times cosine W1t plus theta, and Y2 is A2, that's A sub 1, A2, A sub 2 times cosine of omega 2 t plus theta 2, that's theta 1. So this is theta 1 and theta 2 look just the same, the form is the same, but these coefficients are different. Okay? So what I want you to do is to simply add them up. Take the total is y1 plus y2. Now the little bit tricky thing is that you're going to do it for particular times, for a particular time t. And what I want you to do is, essentially this is going to, so it's going to be A1, and I'm putting in here what the parameters are for A1, omega 1, and T1. So basically, this total is going to be a function of time plus A2 okay. So I'm giving you what these parameters are. This parameter is that, these 6 parameters are, and what your job is to add them up for different times. So you take, and I tell you what to do. I take t equals 0, and always allow delta t to be the exact same number, 0.015 seconds. So that's t, the first t, call it t1. t2 will be t1 plus this delta t. Okay. t3 will be t2 plus delta t. So essentially, the first delta t, the first time, is 0.015 seconds. The next time, the first time is 0. The second time is 0.015 seconds. The third time is 0.030 seconds, and so on. I keep on going until you get the final time. This will be dot, dot, dot. The final time is 0.015. Oops, I just did the wrong thing. I'm sorry. Delta t here is 0.0005 seconds. So the first time is 0.005. The next time is 0.0010. And go all the way down until your first time is 0, the last time will be 0.015 seconds. Hope I didn't get that too confusing, but and you can do it by hand or you can do it by Excel, and I think Excel will be much better because it's much quicker. And then I want you to graph it. And the graph should have all three waves superimposed. For instance, if that's y1, y2 may be something like this, and y3 will be something else. And so I want you to superimpose what these graphs are. And of course, this is time. And the time will go from 0 seconds all the way out to 0.015 seconds. And what you're doing is you're plotting different points. And then you just draw a line right through them. Well, this is a rather long lab. There's a lot to it. There's some very interesting aspects to waves, and which is why this is a rather lengthy lab. But if you have any questions, you can call me or email me. God bless you. Talk with you later. Bye.